are coming to the last bit for this week, and that's what the people call abstract Fourier series, right? So let's come back to where we finished in the previous presentation. So we have got an orthogonal system of functions on an interval, and they are real or complex valued, and we suppose that there will be some well-designed system of constants Cn, which will just give us a convergent power series, and we can expect that the series will converge uniformly, right? Why not? So that is now as an assumption, right? It's not true always, but say it uniformly converges for all the x's in the interval. And by the uniform convergence, it means that we can compute the scalar product of the left hand side with the members of the orthogonal system, which can jump into the sum, right? Because of the uniform convergence. That's something we proved recently or met recently. And then of course the constants will pop up, will jump out from the integral, and what we get is only the scalar product of the couples of the functions, and we know they are always zero except if m is n. So you see that the scalar product of the resulting uniform convergent power series f with any of the orthogonal system functions fn is just exactly the coefficient Cn times the norm of fn. So we know that simply we can compute the coefficient Cn from the scalar product by dividing it by the norm, right? So that's absolutely perfect. And now still a big question remains, because now we've got the main theorem I go through, and I will leave you with the reading through the proof then, which is just repeating and coming back to the other course and thinking about what was happening there with the scalar products and the message that if you want to approximate something the best way in a subspace, then the only way is to take the orthogonal projection from the one point, the one vector, to the subspace. And this is computed in a very easy way if you know the orthonormal frame or orthogonal frame of the subspace, right? You simply write down the coefficients directly for the foot point of the projection. So here we define, as we saw already, what the Cn must be. So that's if we get the orthogonal system, and if we get some function g which we want to approximate via the orthogonal system via a series, then we can write down the coefficients directly. They must be this way if the series approximating it completely would exist, and if it would converge uniformly. So let's assume that, right? In any case, for all the S0 inputs, this integral will exist. So this is a well-defined coefficient Cn. So why not to take it? And now what we take is that automatically the partial sum of the sum we deal with will be exactly the best approximation which is obtainable from the first n functions in the orthogonal system. So this is the first thing. So we can't do any better than this in terms of the chosen norm, L2 norm, right? Then a very interesting observation which comes up is that if I take a sum, now it's not a series, it's a sum of scalars, right? So I take the norms of the fn square. So if it was an orthonormal one, it would be just once here, and I take the squares of the absolute value of the constants Cn, and this sum always converges. And moreover, there is the so-called Bessel inequality, which says that actually the result of this sum, which is always convergent, absolutely convergent, because it's just a sum of positive or non-negative reals, is always less or equal to the norm of G. The norm of G exists because the G is from S0. So that's the Bessel inequality. And then there is the so-called Parseval equality, which says that actually the equality holds if and only if the sequence of partial sums converges to G in L2 norm. We do not say anything about pointwise convergence. We just say that it does converge as the sequence of partial sums in the L2 norm, which is actually something which is much more pleasing. Well, we should also like to know whether it pointwise converges, but this is even more interesting. And to understand this, it's a very straightforward thing, right? The proof is also straightforward. It's a direct computation, more or less, and it just resembles the same observation and intuitive, say, picture that this guy is actually something like the norm of the resulting function, right? So if I take the partial sum of these, it will be always the norm of Hn, right? A square of the norm of Hn. And I simply say that the square of the norm of Hn always converges to something. Well, this is easy to compute, and because clearly the Hn was created by projecting the G. You can always imagine that you take the n elements Fn from your orthogonal system that spans an n-dimensional space. I add the G, and the G together with them will span maybe n plus 1 dimensional system. And then I look at the best possible approximation of G as the partial sum Hn, and what happens? I will take the orthogonal projection of G there. That's what I compute. That's how we computed the CIs in this finite dimensional space. So it's actually what I'm telling now is a full proof. And with such a case, so you are projecting something in finite dimensional space, the projected point was already in the subspace if and only if its norm doesn't shrink after the projection. Right? So it's always smaller. That's the Bessel inequality, and it always is equal if and only if it doesn't shrink. And the point is that the G, if it's not only given by a finite sum, is always shrinked in norm when projected to the partial sum. But if it's possibly approximated in the L2 norm, then in the limit procedure it must not shrink anymore, right? And that's the result. So that's the full explanation of what the abstract Fourier series do. And if you imagine, for example, with the Legendre orthogonal polynomials, then sure, this would be a way how to approximate every integrable thing in the S0, they are all integrable there, by polynomials. And even if it's jumping, so you will always find polynomials which make the jump closer and closer, right? Yes, and in the end we shall get some power series which will be converging by the values to the original function G in L2 norm. Maybe not pointwise in the jumps, if it's really only piecewise continuous, right, the G, then it might be that simply in the individual points it won't. So that might be a correct. But in order to imagine what can we approximate and what we can't, right? So imagine, for example, that we would simply take the Legendre polynomials but skip all of those of odd powers, and keep only those of even powers. So all the functions we will have in our orthogonal system will be, or orthonormal system will be, all the functions will be even. So of course, if I then use them to approximate, say, things on interval -1, 1, then I can hardly expect that anything which behaves as an odd function could be reasonably approximated, right? It would be a problem. So because everything on the right hand side, every of the hn will be an even function. So if I want to approximate an odd function, I fail, right? So you see, it has got some fine points. So thanks, that's all I wanted to tell in this week, and we are finished.